Welcome to Tech Girl Kannada YouTube channel. Boolean Algebra and Logic Gates. Convert the binary into decimal form. This is the binary. We have 1 into 2 power 5, 1 into 2 power 4 plus 1 into 2 power 3 plus 0 into 2 power 2 and so on. If we add all those things, we'll get the decimal value. We have 1 into 2 power 2 plus 0 plus 2 in 2 power 0 is 2 into minus 2. We'll be getting the decimal value. Base 5 examples. 4 into 5 power 3, then 0 into 5 power 2, base 16 examples. B is 11. B into 16 power 3 plus 6 into 16 power 2. Convert the decimal number to binary equivalent. We have 41, 2 20s are, 10s are, and 5s are, 2s are, 2 1s are. So we have to take from this order. A remainder is 1, the remainder is 0. We have to take the remainder as it is from below. 1 0 1 0 0 1 is the answer. For point things 25, we should add it up as 1 1 0 0 1. Therefore binary equivalent of 25 is 1 1 0 0 1. Then point, now consider the fraction, that is 0.375. We have that as 0.375 into 2 is 0.75. 0, whatever is there in the before point, that should be taken. 0.75 into 2 is 1.5. 1. 0.5 into 2 is 1.01. Then 0.0. We have to read it down. This one we should read it up. The binary equivalent is this. The conversion form decimal to any case, any base R system is similar to the above example. 8 1 3. So that is 2 3 1 to the base 8. 8 6 7 8. 8 6 7. We have to divide it and we'll keep the remainder beside. So it will give us this. After it tends to 1, we should clear it as read up 1543 to the base 8 is 867. 0.513. 8 base 8. 0.513 into 844. 0.104 into 8. Then we should read it down. So we have 0.406517 to the power 8 dot 8. Then octal and hexadecimal numbers. The conversion form and to binary, octal and hexadecimal plays an important part in digital computers. Since 2 power 3 is 8, 2 power 4 is this. Binary to octal. We should divide it into the 3 digit numbers. Before point we should take in this way. After point we should take in this way. If we consider 0, 1, 1, that is taken as 2, 1, 2, 4 and 8. 8 is not needed here, so they are taking it as 0, 1, 1 is 3. Then 1 and 4 is 5, 1 is 1. 4 and 2 is 6, 1 is then 2. We have to think of it as 1, 2, 4, 8. 8, 4, 2, 1. Since 8 is itself is octal, we are not considering it here. 7. Next, convert binary to hexadecimal. Consider 4, 4 here. 8, 4, 2, 1. We have, that is 8 plus 2 is 10 plus 1, 11. 11 is B. So we have to see 6B point F2 16. Conversion of octal to hexadecimal. So I have given octal. Octal has been given here. So here 6 can be written as 1, 1, 0, 1, 1, 1, then 0, 1, 1. 1, 1 can be written as this. Then converting hexadecimal to binary. We have to take the 4 digits now. 0, 0, 1, 1, 0, 0, 0, 0, 0, 1, 1, 0, dot 1, 1, 0, 1. That is D. Complements. Complements are used in digital computer for simplifying the subtraction operation for logical manipulation. There are two types of complements. One is R's complement, another one is R minus 1's complement. For binary numbers, 2's complement, 1 complement. For decimal numbers, 10's complement, 9's complement. When the value of base is substituted, the two types receive the names 2's and 1's complement of binary numbers, or 10's and 9's complement of the binary number. The R's complement, given a positive number n, to the base r with an integer part of n digits. Yes. So the R's complement of n is defined as r power n minus n for n is not equal to 0. Positive number n. Integer part is n. So r power n minus n. Now 10's complement of 52520. We have r is 10. How many integer part is 5? 10 power 5 minus 52520. We will be getting this. We have this. Then the 10's complement of 0. There is nothing here. So r is 10's complement. 10 power 0. That is 1. So 1 minus 0.3267 gives 0.6733. No integer part. Tens complement of this can be written as, the integer part is having only 2 digits, so 2, 10 power 2 minus 25.69 gives this 2's complement. The 2's complement of 10110 here 2 power 6. Since 2 is r and the digits is 6, so 2 power 6 minus this, we will be getting 0100100. Then the 2's complement of 0.0110 is, since there is no integer part, 2 power 0 minus we have 0.0110. Give positive numbers n in base r with an integer part of n digits and a fraction part of m digits. The r minus 1's complement of n is defined as r minus 1's complement, r power n, r power m minus n is r power minus m. Okay, n is positive number, base is r, integer part is n, fraction part is m. So r minus 1's complement is of n is equal to r power n minus r power minus n minus n. The 9's complement of 52520. We have 10 power 5 minus, there is nothing here on this 0. So 10 power 0 is 1. 1 minus 52520, it is 47479. No fraction part. Yes. The 9's complement of the 0.3267, 10 power 1, 10 power, there is no integer part, 10 power 0, it is 1. So minus, again r is 10, so 9, r is 9, here r is 9, not 9, r minus 1 means it is also 10 only. 10 power, since there is 4 digits after decimal, we have to put minus 10 power minus 4 minus 0.3267. We have this, no integer part. And again 9's complement, 25 point, this is 25, so 10 power 2 minus 10 power minus 3 minus this number gives you 9's complement. 1's complement, we just have to take this as 1's complement, that is 2 power 6, there is no that digits 2, so 2 power 0 minus 10110. We got the same. Now there is a decimal point here. How we have to work along this? So we have decimal point as 0.0110. So 2 power 0 minus 2 power minus 4. Then again minus, it is 0.0110. Here we have in binary form, normal form, we have 1 minus 2 power minus 4. So this comes to something here. In decimal we got 0.9375 whole to the 10. So we have to make it as if in like to binary form. So we have it as 0.9357 into 2. Convert it into binary form. Next 0.875 into 2, and this into 2, this into 2 will getting 1. Then 0 into 2, obviously it will be 0. So 0.1111. So we have 0.1111 minus 0.0110 will be getting it as 0.1001. Yes. Subtraction with r's complements. The subtraction of two positive numbers m and n, both of base r, may be done as follows. Add the minuend to the r's complement and subtrahend n. Inspect the result obtained in step 1 for an end carry. If an end carry occurs, discard it. If an end carry does not occur, take the r's complement of the number obtained in step 1 and place a negative sign in front. Using tens complement, subtract 72532 minus 3250. We have, find the tens using tens complement, subtract this into this. Okay, we have to find the tens complement of n first. What is tens complement of n? That is by working of this n, tens complement of n is equals to 10 power 1 2 3 4 5. Okay, 10 1 2 3 4 5 minus 10 power 5 minus n gives 96750. Here end carry is 1. Ignore carry. We have to add these things. If an end carry occurs, discard it. If an end carry doesn't occur, take the r's complement. Add the minuend to the r's complement of the subtrahend. Then m is the minuend. Whatever they gave on from is the minuend. Seven 2532. Then we need to add this. 72532 plus 96750. We have 169,282. End carry is 1. So we need to get only 5 digits. We have got it. Ignore carry. Answer is this. Using tens complement, subtract 72532 from 320. That's already done. Using tens complement, subtract this. from this. Yeah, it is given as minuend is 03250 minus 72532. Here it is taken as tens complement of n. That is 72532's tens complement is r power n. That is 10 power 5 minus this number gives 10 power 5 minus 72532 gives 27468. That is taken as tens complement. Then we need to add this to minuend plus 3250. We will be getting 30718. There is no carry, so we have to take the complement of this number. So the answer will be 30718 complement 10 power 5 minus 30718. It will be 69282. It is minus tens complement of this. It is minus 69282 minus should be sign should be changed. Using complement subtraction 1000100 from this. Using 2's complement subtract this from this. Then now minuend subtrahend n subtrahend 2's complement of subtrahend. We have to take the 2's complement of subtrahend. That is nothing but the first two digits will be same, first three digits. Then we will be changing 1 1 1 and 0. That is the 2's complement. Next, for 2's complement we need to add the minuend. If we add this 1 0 1 0 1 0 0. Okay, for this we have to take it as base number, that is this binary, and 1 0 1 0 1 0 0 plus 0 1 1 1 1 0 0. We will be getting 1 0 0 1 4 times 0, but we have here only 7 digits. Here there are 8 digits, so 1 is a end carry. Then 1 4 times 0 is the answer. Using 2's complement, subtract this. This is minuend, this is subtrahend. Then we should find the n's complement. N's complement is 0 0 1 1 0 1 0. Correct. Again, if we go to this base number binary, we should add both of them. 1 0 0 0 1 0 0 plus 0 1 0 1 1 0 0. We will be getting 111 4 times 0. There are 7 digits. The answer is also 7 digits. There is no carry. we have to take the complement of this as answer. Minus complement. We have this. Then we have to take the complement of this. What is complement of this? 2 power 7 is 128. So 2 power 7 minus this. $128. In binary form it is given as this. Next we should minus by this number 1110000. We will be getting 1000 and we should make it as minus 1000. Subtraction with r minus 1's complement. Subtraction of m minus n. Subtraction with r minus 1's complement. Add minuend to the r minus 1's complement of subtrahend of n. Inspect the result obtained in step 1. If the end carry across, add 1 to the least. If the end carry occurs, add 1 to the least significant digit. If an end carry doesn't occur, take r minus 1's complement of the same number and obtained in step 1. Place a negative sign in front of it. Here we have seen this. 9's complement of this can be taken as 9's complement of n. It is r power n minus r power minus n minus n. It is 10 power 5 minus 10 power minus 0. 0 is 1. Minus this number 3250, which gives us 96749. Here, by adding this to minuend 572532, we get 169281. 281 we will be getting. Since the end carry is 1, there should be 5 digits only. The end carry should be added here. In r's complement, it will be neglected. But here we should add it. That is 69282. 9's complement of same thing, but in different way. Then we have to find the 9's complement of 7 to this. 10 power 5 minus, there is no any digit, minus this number 72532, which gives us 27467. There is no carry. Also, even this, for this we should add the minuend 3250. We are getting 30717. There is no carry. We have to find again the 9's complement of 3077. 10 power 5 minus 1 minus 30717. 69282 minus 69282. We have this. Using 1's complement, find this minus this. They've been already given that. To find the 1's complement of n, that is 2 power 1, 2, 3, 4, 5, 6, 7. 2 power 7 minus 1 is 127. So we have to take this to the baseline. 127 equals to, and then we need to add m minuend 1010100. That is equal to something called 1 1, so it is 1000. Next, using 1's complement, subtract this. First procedure, we should find the complement of n. Then we have to add it to the m. We will be getting some answer. We should see whether it is having carry or not. If it is having carry, in r minus 1's complement, we should add it to the answer. Then if there is no carry, then we have to take the complement of it, and answer should be in this. Minus 1000 is the answer. Working is already being provided here. 1's complement of this number, that will gives you this. Then basic definitions. Boolean algebra, like any other deductive mathematical system, may be defined with a set of elements, a set of operators, and a number of unproved axioms or postulates. Boolean algebra. Set of elements, set of operators, and number of unproved axioms and postulates. If S is set and X and Y are certain objects, as X belongs to S denotes X is a member of set S, Y belongs to S denotes Y is not an element of S. Definition: binary operator. A binary operator defined on a set S of elements is a rule that assigns to each pair of elements from S a unique element from S. Binary operator is on a set is an element of it is a rule that assigns to each pair of elements from S a unique element from S. For example, consider the relation A into B is equals to C. We say that into A is a binary operator if it specifies a rule for finding C from a pair of A, B, and also A, B, C belong to set S. However, star is not a binary operator if A, B belongs to S, while the rule finds C is not belongs to S. Then star is binary operator A belongs to A star B is equals to C if A, B, C belongs to S. It is not a binary operator. A, B belongs to S, but C doesn't belong to S. Most common postulates used for formulate various algebraic structures are closure. A set S is closure with respect to binary operator F. For every pair of elements of S, the binary operator specifies a rule for obtaining a unique element of S. For example, the set of natural numbers n, 1, 2, 3, and 4 is closed with respect to the binary operator plus by the rules of arithmetic addition. Since for any A, B belongs to n, we obtain a unique C belongs to n by the operation A plus B is equals to C. The set of natural numbers is not closed with respect to the binary operator minus by the rules of arithmetic subtraction, because 2 minus 3 is minus 1 and 2, 3 belongs to n, but the minus 3 doesn't belong to n. Associative law. The binary operator on a set S is said to be associative when x into y into z is equals to x into y into z. If A, B belongs to n, closure property, the set is closure with respect to binary operator every pair of elements the binary specifies a rule for obtaining a unique element S, which is not closed here. Associative law, commutative law, x into y is equals to y into x, where all x, y belongs to S. Identity, E into x is equals to x into E. Identity. Inverse x into y is equals to E. Inverse the set A having identical element E with respect to A binary operator into is said to have an inverse whenever for every x belongs to S there exists an element y belongs to y such that x into y equals to E. In the set of integers I is equals to E, A plus minus E is equals to 0. That is inverse. Distributive law A in V into y dot C is equals to x into y dot x into z. Or we can also take it as x plus y dot z is equals to x plus y dot x plus z. State axiomatic definition of Boolean algebra along with the postulates. Axiomatic definition of Boolean algebra. A two-valued Boolean algebra called switching algebra. Definition: Boolean algebra is an algebraic structure defined on a set of elements. Algebraic structure defined on a set of elements B together with two binary operators plus and dot, provided the following Huntington postulates are satisfied. Closure with respect to the operator plus, closure with respect to the operator dot. Identity element with respect to plus should be designated to 0. Identity element with respect to dot should be designated to x. Designated by 1. Commutative with respect to plus, x plus y is equals to y plus x. Then commutative with respect to this could be x dot y is equals to y dot x. Then dot is distributed over plus, plus is distributed over dot. X dot y plus z. Okay, then for every element x belongs to B, there exists an x dash belongs to D and called the x dash is its complement, such that x plus x dash is 1, x dot x dash is equals to 0. There exists at least two element x comma y belongs to B such that x is not equal to y. The valued Boolean algebra show that the Huntington postulates are valid for B is equals to 0, 1. Huntington postulates. The two-valued Boolean algebra is defined on the set of two elements B is equals to 0, 1 with rules for the two binary operators plus and dot as shown in the following operator tables. X, y, x dot y, x, y, x plus y, x, so x dash. It is taken as 0, x dot y 0, 0, 0. X plus y it takes you to the AND gate. These rules are exactly the same as the AND, OR and NOT operators, respectively. We must now show that the Huntington postulates are valid for set B 0, 1 and the two binary operators defined above. Closure. Closure is obvious from the table since the result of each operation is either 1 or 0. 1, 0 belongs to B. From the table, we see that 0 plus 0 is 0. Each establish the two identical elements 0 for plus and 1 for dot is defined as postulate 2. Commutative law says that are obvious from symmetry of the binary operator tables. A distributive law x dot y plus z is equals to x dot y plus x dot z can be shown in the below truth table. For each combination, we derive this same. For each combination, we derive x dot y plus z and show that the value is same as x dot y plus x dot z. Here it is clearly seen that the distributive law of plus over dot can be shown hold true by means of truth table similar to that one above. From the complement table, it is easily shown that x is equals to 1, x plus x dash is equals to 1, 0 plus 0 dash. It is 1 and 1 plus 1 dash is equals to 1. 1 dot 1 dash 1 dot 0 is 0. Which what is this postulate? Postulate 6 is satisfied because the two-valued Boolean algebra has two distinct elements 1 and 0 with 1 not equal to 0. Basic theorems and properties of Boolean algebra. It states that every algebraic expression deducible from the postulate of Boolean algebra remains valid if the operators and identity elements are interchanged. If the dual of algebraic expression is desired, we simply interchange OR and AND operator and replace ones by zeros and zeros by ones. Basic theorems. The below table lists 6 theorems of Boolean algebra and 4 of its postulates. The theorems, like the postulates, are listed in pairs. Each relation is the dual of the ones paired with it. The postulate are basic axioms of algebraic structure and need not to prove it. The theorem must be proven from the postulates. Here is the table. We can see. Here is the table we can see. Postulates and theorems of Boolean algebra. Postulates 2, that is x plus 0 is equals to x dot 1 is equals to x. Postulate 5, that is x plus x dash is equals to 1, x dot x dash is equals to 0. Theorem 1, x plus x is equals to x dot x is equals to x plus 1 is equals to 1, x dot 0 is equals to 0. Involution theorem 3, x complement whole complement is x. Postulate 3 is commutative, x plus y is equals to y plus x, xy is equals to yx. Associative, x plus y plus z is equals to x plus y plus z. xyz is equals to xy into distributive, x into y plus z is equals to xy plus xz. X plus yz is equals to x plus y dot x plus z. DeMorgan, x plus y whole complement is x complement y complement. xy whole complement is x complement plus y complement. Absorption, x plus xy is equals to x. X into x plus y is equals to x. Theorem 1a, x plus x is equals to x. How it is possible? X plus x dot 1, x1 can be written as x plus x dash. So x plus x into x dash gives 0. That is x. Theorem 1b, it is x dot x is equals to x dot x plus 0. 0 can be written as x dash. So x into x plus x dash is 1x. Now 1b is dual of theorem 1a. Now 2a is x plus 1 is equals to 1. 1 into x plus 1. 1 can be written as x plus x dash. X plus x dash into 1. What is x plus x dash? X plus 1 is equals to 1. Then x dot 0 is equals to 0 by duality. Then from postulates we have x plus x dash is equals to 1. X into x dash is equals to 0. We define the complement of x. In this, the complement of x dash is x and is also x complement whole complement. Therefore, since complement is unique, we have that x complement whole complement is equals to x. So theorem says x plus xy is equals to x. X dot 1 plus xy. So x into 1 plus y. 1 plus y is 1. So x dot 1 is x. Theorem 6b, x into x plus y is equals to x. X plus xy is equals to x. X into x plus y is equals to x. So this can be shown in the below table, truth table. X into x plus y, that is x plus xy. X into x plus y, both are same in this. xy, x plus xy. Then DeMorgan's theorem, state and prove DeMorgan theorem for two variables. There are two laws, that is x plus y whole complement is x complement dot y complement, and x dot y whole complement is equals to x complement plus y complement. For two variables, the truth table is given below. Venn diagrams. Venn diagram is used to visualize the relationship among the variables of Boolean expression. Hence the Venn diagram. The diagram consists of rectangle, such as this figure, inside of which are drawn overlapping circles, and for each variable, each circle is labeled by a variable. We designate all points inside a circle as belonging to the named variable and all points outside a circle as not belonging to a variable. Example, the circle labeled x, if we draw inside, then the area belonging to the inside the rectangle, the area not belonging to the either x or y. This can be further understood by the problems. Here is an example, Venn diagrams. It is x, y dash, x, y together, and x dash y is present. The space outside the circles are x dash, y dash. There is no x or y. Venn diagram of two variables. Venn diagram may be used to illustrate the postulates of Boolean algebra to show the validity of the theorems. Figures of our example illustrates the area belonging to the xy is inside the circle x, and therefore x plus xy is equals to x. Venn diagram for distributive law, x into y plus z is equals to xy plus xz. Distributive law. Next is Boolean functions. The binary variable x, y, z can take the values of 0 or 1. The binary functions, binary variables, two binary operations or and, the unary operator not, parenthesis and equal sign. If n is x, y, z dash. These are the Boolean function will also be represented in the truth table. N binary variables will be having 2 per n combination of ones. So we can see here f1 is x, y, z dash, f2 is x plus y dash z. And then we can also see this as x dash, y dash, z dash. f2 is equals to 1 if x is equals to 1. If y is equals to 0, then z is equals to 1. f3 is x dash, y dash, z plus x dash, y, z. This is same as for f3 and is considered below. Truth table can be considered as for this. Truth table for f1 is x, y, z, and f2 is x plus y dash z. f3 is x dash, y dash, z plus x dash, y, z plus x, y dash. f4 is x, y dash, x dash, z. Then if we consider, we will be getting the answer as this. Then we can also maybe transform them into algebraic expression into a logic diagram. Since there is a multiplication, we will be using AND gate. AND gate which gives x, y, z dash as f1. Then again x plus y dash z. Y dash z is represented as y naught and the z taken into AND gate. Again that is taken into OR gate along with the x. So x plus y dash z, that is f2. Then for this it is x dash y dash z plus x dash y z. f3. Here also x y dash plus x dash y. Algebraic manipulation that can make into minimal literals. That is x plus x dash y. X can be written as x plus x dash y. This can be written as x plus x dash dot x plus y. X plus x dash is 1, so it is x plus y. This can be written as x into x dash plus x into y, that is xy. then x dash y dash z plus x dash y z plus x y dash. This can be taken as x dash z y plus y dash plus x y dash. That is x dash z plus x y dash, x y plus x dash y, x dash z plus y z, x y. We are having this as x y x dash z. Since there is no x in the third term, we are using y z into x plus x dash. That is x y x dash z, x y z, and plus x dash y z. We have same as this x y 1 plus z is 1 plus x dash z is 1 plus y is 1, then x y plus x dash z. So x plus y into x dash plus z into y plus z. By duality from this we have x plus y into x dash plus z by duality from function 4. What is the complement of this function f is dash? What is the complement of this function? That can be taken as a plus b plus c whole complement is equals to, let us take it as a plus x b plus c as x, a plus x whole complement is equals to a complement x complement, that is b plus c whole complement, that is b complement c complement by DeMorgan's theorem. For any number of variables can be written as this, and in the generalized form this can be taken as this. Find the complement of the function x plus x complement yz dash plus x dash z y dash z. First we'll consider the f1 complement. First we take this as only the plus symbol. A plus b whole complement is a complement b complement. Then if you consider this, we'll be having those complement of x dash is x plus y dash plus z dash into x plus y plus z dash. X into this is whole complement is x complement plus this complement, and here is the final complement of the functions f1 and f2. A complement plus b complement. This is the duality of a plus b whole complement. And we can also make it as into. The main thing is we should put the plus sign in place of multiplication. We should put the multiplication sign in place of all addition and complement of each variables. Canonical and standard forms, two types. Sum of mean sum, product of max terms. Mean terms and max terms. The binary variable may appear either in its normal form or in its complement form x dash. Now consider two binary variables x and y combined with an AND operation. Since each variable may appear in the either form, there are four possible combinations: x dash y, x dash y, x y dash x y. Each of these four AND terms represent one of the distinct areas of the Venn diagram and is called. Similarly, for n variables, each of our AND terms, mean term, a standard product. This is in standard product term, product of mean terms. Similarly, for n variables can be combined to 2 power n mean terms. For 3 variables, the symbol for each mean term is also shown in the table is of form mj, where j denotes the decimal equivalent of the binary mean terms decimated. In a similar fashion, n variable forming an OR term with each variable being primed or unprimed provides 2 power n combinations called max term. Similarly, OR term. The n variables forming OR term with each variable being primed or unprimed provides 2 power n combination of max terms. Those are standard sums. The 8 max term for 3 variables, together with the symbolic designation are listed in the table. Now that each max term is complement of its corresponding mean term and vice versa. Mean terms and max terms for 3 binary variables. Mean terms and max terms. Mean terms are x, y, z. Mean terms, max terms. We know that input has 4, 2 and 1. So here we have x dash, y dash, z dash, x dash, y dash, z, x dash, y, z dash. In the same way, m0, m1, m2, m3, m7 should be taken. For max terms, we take the complement of that forming OR of term. That is x plus y plus z and x plus y plus z dash, which gives the max terms m0, m1, m2 and all. The Boolean function may be expressed algebraically from a given truth table by forming a minterm for each combination of variables, which produces a 1 in the function, and then taking the OR of all those terms. For example, the function f1 in the table 2 to 4 is determined by expressing the combinations 0, 0, 1, 1, 0, 0, and 1, 1, 1. 0, 0, 1, 1, 0, 0, 1, 1, 1. This is taken as x dash, y dash, z, x, y dash, z, and this. So if we write the table, we'll get to know that function of 3 variables will be in AND operation during OR operation. AND operation we multiply 0, 0, 0, 0, 0, 0, 0, 0. Function 2 0 plus 1 plus 1. 0 ones are 1. Now how it becomes 1? No, it is 0 only. 0 plus 1 is 1, 1 plus 1 is 1. Then here it gives the same different values. By these tables, we consider it as m3, m5, m6, m7. We can conclude any Boolean function can be expressed as sum of min terms. That is meant by ORing of terms. Complement of the Boolean function. We take the complement of whole thing. We adjust it into m0, m2, m3, m5, m6. Similarly, these things m0 dot this m1, m2, m4 and all. Next, we can conclude any Boolean function can be expressed in terms of product of max terms. By product is meant by ANDing of terms. Boolean functions expressed as sum of mean terms or product of max terms are said to be in canonical form. Sum of mean terms. Express the Boolean function as sum of min terms. A plus b dash c is still missing one variable. So a can be written as b a into b plus b dash, a b plus a b dash. We are still missing one more variable, that is c in each. We can write it as a is equals to ab into c plus c dash plus ab dash into c plus c dash, abc dash plus ab dash c plus in b dash c we are missing one variable, that is a. We can write it as a plus a dash. Combining all, we have a plus b dash c as abc plus abc dash plus ab dash c, ab dash c dash plus ab dash c, a dash b dash c. A b dash c appears twice, So remove one of them. Rearrange mean terms in ascending order. So we will be getting mean term as sigma of all those numbers. Product of max terms. Xy plus x dash y. First convert the function into R terms. We can make it as xy plus x dash into xy plus z. Then again we should consider it for x plus x dash into y plus x dash, x plus z into y plus z, x dash y into x plus z into y plus z. The function has three variables x, y and z. Each atom is missing one variable. So x dash y can be taken as x dash plus y plus z z dash. That is x dash plus y plus z into that thing. X plus z into x plus y plus z. Y dash plus z. Combining all the terms and removing those that appears more than once, we finally obtain the answer as this in terms of min terms and max terms. Conversion between canonical form. Two types of canonical forms are sum of min terms and product of max terms. The complement function expressed as the sum of min terms equals to the sum of min terms missing from the original function. This is because the original function is expressed by those min terms that make the function equal to 1, while its complement is 1 for those min terms that function is 0. As an example, conversion of this f of abc equals to 1, 4, 5, 6, 7. Sum of mean terms. Take a complement of f. F dash of abc is min terms of 0, 2, 3. So f dash is equals to m0 plus m2 plus m3. Let's take a complement of f dash whole dash. We will be getting the same answer as this. m0 plus, let's take a complement of this, sum of min terms. We will be getting m0 dot m2 dot m3. Then pi of 0 to 3. Product of max terms. This can be expressed in the product of max terms. So f of abc is equals to pi of 0 to 4, 5. Product of max terms, that is abc is equals to, since these are the max terms, we need to do product. m0 dot m2 dot. So f dash of abc is pi of 1, 3, 6, 7. Then again f dash of abc is m1 dot m3 dot m6 dot m7. Take complement of f dash. We have f of abc, that is m1 dot m3 dot m6 m7 whole complement. So m1 dash plus m3 dash plus m6 dash plus m7 dash. mg dash is equals to mj. So that is m1, m3, m6 plus m7, sum of mean terms. There are two ways of expressing Boolean functions, that is canonical form, standard form. Canonical forms, two types: sum of mean terms, product of max terms. Standard form, sum of products. Sum of products, y dash plus xy plus x dash y z dash. Then product of sum, x into y dash plus z into x dash plus y plus z dash plus w. Canonical form. The two canonical forms of Boolean algebra are basic forms that obtains from reading a function from the truth table. These forms are very seldom the ones which the least number of literals, because each min term and max term must contain the definition all the variables either complemented or uncomplemented. Another way of expressing this is standard form functions. In this configuration, the terms of a function may contain 1, 2 or any number of literals. So that is this. There are two types of standard form: sum of products and the products of sum. The sum of products is a Boolean expression containing AND terms called product terms of 1 or more literals, the sum denotes the ORing of these terms. An example of function expressed in sum of products is y dash plus xy plus xy. Product of is product terms of 1, 2, and 3 literals, each respectively. Their sum is effect and or operator. The sum of products is expression containing and terms called product terms of 1 or more literals. This is ORing then. Then product of sums. The product of sums is a Boolean expression containing all terms called sum terms. Each term may have any number of literals. The sum denotes ANDing. The product denotes ANDing of these terms. Example of a function expressed in terms product of sums is this. This expression has 3 sum terms of 1. Product is an AND operator. It is a canonical form as well as the standard form. It is not the canonical form, it is standard form. It is a canonical form and the standard form. It is not a canonical, it is standard form. Other logic operations with the binary operators and or are placed. Here you can see the truth table. 2 power 2 power 2 functions for n variables. 16 possible functions, that is f0 to f15 is here. Then the Boolean expression for 16 functions. Here is the expression for 16 function of 2 variables. You can go through that. Then we come to this digital logic gates. Name and date xy. Algebraic function xy. Truth table 0 plus 0 0. 0 plus, it is xy multiplication. 0 plus 0 into 0 0. 0 into 1 0. 1 into 0 0. 1 into 1 is 1. Or operator x plus y. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is also 1. 1 plus 1 is also 1. Inverter operator, it is x dash. 0 becomes 1, 1 becomes 0. Buffer is 0 will be 0, 1 will be 1, x. NAND operator, xy whole complement. 0 0 1 0 1 1 1 0 1 1 1 is 0. NAND operator. NOR operator, it is x plus y whole complement. That is totally different from OR gate. 0 0 0 1 0 1 0 1 0 0 1 1 is 0. Exclusive OR, XOR operator. Exclusive OR is x y dash plus x dash y, that is exclusive x XOR y. 0 0 0 0 1 1 1 0 1 1 1 is 0. Exclusive NOR or XNOR equivalence operator, that is xy plus x dash y dash. X circle inside the dot, that is XNOR operator. XOR operator and XNOR operator, that is 0 0 1 0 1 is 0 1 0 is 0 1 1 is 1. Digital logic gates.
Thank you for watching. Do like, share and subscribe to my channel.